Looking at another specific feature of the ITCZ that occurs in regions where there is a cross-equatorial pressure gradient that's strong. We talked about the Indian Ocean, so this is the June, July, August. You have cross-equatorial gradient that's very strong, but there is no rain there. We get the marine ITCZ and this complicated mess here with orographic rain on the Western Ghats, Himalayas, Bay of Bengal, Burmese mountains, and so on. And in the winter months, there is this the great cloud band, kind of a version of SPCZ on this side. So, just to briefly look, if you look at the East Pacific, the Indian Ocean, and this is DJF, this is JJA, and the Atlantic Ocean during JJA. There are these westerlies that are typically interpreted as just winds crossing and then following Coriolis. In the northern hemisphere you get tilted to the right, to the left in the southern hemisphere, but it turns out that that's not enough to explain the strong westerlies. In fact, climatically speaking, these westerlies here are very critical because they create a wind stress curl and lift the thermocline and are very critical for genesis of MJOs and various other things, climatically important region, cyclones, Rossby waves, and so on and so forth. So the idea is that the cross-equatorial advection has to be split into the divergent part and the rotational part. As you know, non-divergent, you can define a stream function and so on. So that's how the subscripts come from. So writing our potential, the absolute total vorticity conservation equation, starting with the total, we're looking at advection of the vorticity, vortex tube stretching, and the dissipation term. Looking again at the place where eta is 0. So there you have data dt equals 0, and the terms advection and tube stretching should balance the dissipation term. The divergent part is 0 at that, is close to 0 at that point. As you remember, winds are accelerating, reaching maximum divergence, and north of the absolute zero vorticity, absolute vorticity 0 line, there is convergence. So you have Vx, V psi going to towards 0. So you have basically the dominant term, the advection by the divergent component balancing the dissipation term on the absolute 0 line. So then you can calculate the momentum balance by integrating that equation, this equation, with respect to latitude, right? Assuming via axis symmetry that Vx, V tilde x is Vx, so the vector is reduced to the scalar, which let's say is a constant, and zeta is minus day u psi, partial u psi dy. That's the relative vorticity. Then you can write v chi as alpha u psi. Okay, so very simple modification, and better to just look at the physics of how that will work. This is the schematic diagram showing the balance of forces in the vicinity of 0 absolute vorticity line, which is shown here in the red line. Okay, and the divergent part of the wind field showing a maximum, oh man, this computer is gonna, okay, maximum sorry, where was I? The maximum in the divergent wind coincides with the eta equal to 0, the contoured red line, rotational part of the wind field where the advection of the gradient of absolute vorticity grad eta by the rotational part of the wind field is 0, where eta equal to 0. That's why we simplified this to this. Okay. The observed location of the low-level westerly jets is shown on the poleward side here. Okay, and in here the distribution of relative verticity and the resultant zonal wind field. So basically you have to still worry about balancing verticity equation, and zonal wind maximum here occurs on the poleward side to be able to match these verticity balance equations. So you have cross equatorial pressure gradient, you have divergence coming in, and you're going to have divergence of the divergent wind part be 0 at the 0 absolute verticity line, and the velocity itself is maximum, and then you have convergence. So you have the rotational part V psi dot grad eta balancing the verticity equation, which requires that you need this meridional shear. Okay, so the vertex tube stretching is going to relate to balance the verticity being advected in at the 0 verticity line. I hope I'm saying it clearly enough. So here is the verticity distribution. Okay, so you have relative verticity and the planetary verticity together going to 0 here, and then the relative verticity dying off because of this meridional shear. This is why you require strong westerlies on the poleward side of the 0 absolute verticity line. Okay, that explains why you have the westerly winds on the northern side of the 0 absolute verticity line, where there is cross equatorial pressure gradient that is very strong. Another very specific regional feature that is described, and we will just kind of go through it and leave it there for now. Okay.